Benish, can you remind to Savi?
Okay, sir.
Okay, yeah. So very good evening to you all. Extremely sorry for starting the late evening lecture. So, so on last Friday, we had a very detailed class over the stone column. So we try to understand under what circumstance the ground improvement technique called as the stone column will be useful. So today, let us take another topic that is on deep dynamic compaction. But if you look at several soil improvement or the ground improvement techniques, a few of them are listed here, like deep dynamic compaction, vibroflotation, vibropire, compaction grouting, lime stabilization, and blasting. If you look at carefully all of these techniques, so majority of these techniques are applicable to granular soils like a sands. Now, I said a technique called as a deep dynamic compaction. Now we know what is the meaning of the compaction because we have understood the compaction in a standard Proctor compaction test or modified Proctor compaction test. But what would be the limitation of the standard or modified Proctor compaction is that, so first of all, we can't able to densify the soils of a greater thickness at the max in a given situation or in a given pass. We can able to densify a 1 feet soil layer. That's it. But of course, you can make any number of layers if the amount of the construction is less. But what if a large area or a deeper depth has to be densified? Like the photo shown in right side bottommost picture. Just see here. Uh, in fact, I want to extend my zone of improvement from the ground surface to several meters below the ground. But I don't want to go, or I don't want to make any borehole into the soil. Rather, if I do something on the top surface or on the ground surface, but I could able to accomplish the more densified state even at a greater depth. Say for example here, if you look at 4 to 8 meter, so 8 meter is not an ordinary depth. If you look at carefully, it's a huge. And just imagine, if I want to pass an energy from the ground surface to a depth of 8 meter, what would be the intensity of the impact that you would create on the ground surface? So this you need to understand. So one of such technique is called as a deep dynamic compaction. So compaction means again densification of the soil. So either you can do the same thing by the conventional compaction, but that we are not discussing here in this case. Now,
Sir, you're not audible, sir. Hello?
hello.
Yeah, hello, sir.
Yeah, am I audible now?
Yes, yes, yes.
Okay. Shall I repeat everything?
For the last 1 minute, sir, we couldn't hear.
That's okay. So what I was discussing is how do you define deep dynamic compaction? When I say the compaction, we understood a bit about the conventional standard Proctor compaction, but that's not what we are discussing here. So compaction by the dynamic process at deeper depths. Deep means I told you 4 to 8 meters or even greater depths. Dynamic means even standard Proctor also is a dynamic compaction. Static means you don't apply the number of blows. You apply only the constant load and you allow to densify the soil sample. Suppose if you apply the same load repeatedly, default it becomes a dynamic. So deep dynamic compaction means you are densifying the soil at deeper depths with the help of repeated number of blows. That's what is the meaning of deep dynamic compaction. Now here this slide will show you different techniques to densify the soil and their depth of improvement. For example, if you look at the dynamic roller compaction, this is the dynamic roller compaction. It is suitable up to a depth of 1.5 meter and it produces some kind of the harmonic, that is vibration. And if I want little deeper depth, so up to 8 meter, then I can go for the impact compaction. So or it is also called as a intelligent compaction or impact compaction. And if I want little further deep, then I can go is deep dynamic compaction. So if you look at this figure, what I do is I will take a very heavy weight, lift it to a certain height, then drop it. So as a result, if I lift a certain tons of the weights and drop it, how much amount of energy, amount maybe in terms of the potential energy that is applied at the ground.
Hello,
Yeah, Vishal.
sir, your voice is lacking, sir.
Oh my goodness. I don't know what is the reason. Maybe network issue. Okay. So anyhow, it is recorded, so no issue. So in case of the deep dynamic compaction, so a heavy weight is lifted to certain height and from there it is allowed to free fall, and then you can see the kind of an impact that creates on the ground. There is another technique that is called as a vibro flotation. So even if you want a greater depth of ground improvement, say up to 60 meters, then we can adopt another technique called as a vibro flotation. So here, so this is the device. So this is called as a vibro float. This is inserted into the ground, and this probe imparts some kind of the dynamic energy in the form of the vibration energy to the sides, to the soil. However, especially in the lateral direction, as these arrows are showing, this excites the particles, especially in the lateral direction. So whenever there is an excitation energy in the lateral direction, so that particles gets rearranged and thereby they will get densified. So this is the fundamental principle of the vibro flotation. But here we use something called as a vibro probe, which will be inserted into the ground. Okay, so these are the four different techniques depending upon the depth of the improvement that we desire, so that we can resort it to any one of these techniques. If it is a shallow, then we can go for dynamic roller, little deeper impact compaction, even deeper deep dynamic compaction, even deeper we can go for the vibro flotation. But now what we are going to discuss is deep dynamic compaction. The technique was developed by Louis Minard in the year 1960. So it is one of the ground improvement techniques to achieve the deep ground densification. So wherever the site where you are envisioning for construction of a building or a road or an embankment or a very heavy structure, especially the granular soil, not the cohesive soil, especially granular soil, there you can use the deep dynamic compaction. That the technique uses dynamic effect of high energy impacts caused by dropping a large steel weight. So here, if you look at this crane carefully, so a very heavy weight, this is called as a tamper. This tamper is attached to the crane. What we do is this tamper is raised to certain meters and allowed for the free fall, or it is dropped from a certain height. That is called as a deep dynamic compaction. So dropping of a heavy weight. So in this picture it is shown, this is the heavy weight. So what would be the approximate weight of this heavy weight? 100 to 400 kilonewton, depending upon the degree of improvement that is required. Then height of the free fall, that is 5 to 30 meter. Again, this depends upon the type of the soil, the depth of improvement required, so on and so forth. So here, even in this condition also, so in case of the deep dynamic compaction, so the ground improvement is achieved by adapting to something called as a grid pattern, maybe a triangular or maybe a rectangular, like the sand rain or the stone column techniques. In fact, those techniques also so adapted in the form of a triangular or rectangular. So this is the fundamental definition. Now here you can see. So another definition: pounding the ground by heavy weight. So this is either called as a tamper or pounder, whatever it is, applicable to all types of granular soils which are able to freely drain the water. So it is essentially useful for granular soils, which may be a natural soils or which may be an artificial fields. In both the cases, this technique is useful, but particularly well adapted for non-organic, non-homogeneous fields. Fields means these are the man-made dumps and made ground, that is artificial ground, reclamation areas and karsta terrain with sinkholes. So for these kind of the soils, deep dynamic compaction is the most suitable. Now, so another specific thing that you can notice from this slide is when a heavy weight is raised and dropped suddenly from a certain height. So for example, just imagine I am raising a 30-ton of heavy weight and dropping from a height of 30 meter. So it is obvious that so upon it reaches the ground and it densifies the soil instantaneously, but at the same time you can witness the formation or the densification of such a thing in the form of a crater, so this is called as a crater. So this crater is created by the impact. So on one side, so in the previous slide we understood that so dynamic compaction means dropping a heavy weight so from a certain height. Now suppose if you look at the cross section, so here the area which is shown in the form of increased arrows, in the form of a dotted lines, but on the ground surface the area of influence is less, but when you go deeper it is increasing. But at certain depth you can also see an overlap of one drop over the adjacent drop. Suppose here you can see, so this area is under overlap, and even this small triangle also under overlap, meaning thereby here in this area it is getting the energy from the three drops. So for example, so this area getting only energy from the single drop. This area or this soil is experiencing the energy from the two drops, while this small triangle is impacted by three number of blows. So three number of blows. Okay, so this is how you can understand how the zone of influence so can be created. Okay, or how to understand when I apply certain amount of energy on the ground surface, how the bottom soil or the soil below the ground surface is getting densified. Okay, so here the difference in heights indicates the formation of the crater. Now this is some kind of an aerial view which is clearly showing the formations of the craters. Now here you can also see the craters were formed or the dynamic compaction was done in some particular pattern. So maybe in a triangular pattern or rectangular pattern, whatever it is. And you can also witness or you can also see from this picture. When you compare, see you can see in this picture a man is standing right on adjacent to the crater. So this is the crater. In fact, the size of the crater is much higher than the size of the man. In fact, the depth of the crater is more than man's height. Now you can understand what could be the impact energy. So if you go for a single blow. So this is the impact of the deep dynamic compaction. Now here, one question that may arise in your mind is it because of the single pound or number of pounds? It may be because of the number of pounds. That means more than one number of a drop. So that is one of the design factor. Now, what is the obvious consequence or significance of this crater? It indicates that the soil right beneath this crater is totally got densified. The formation of the crater means the densification of the soil right beneath the crater. That's what is the meaning of this crater. Okay. So that much volume of the soil underneath the crater has got densified. So here you can see this is another aerial picture of a deep dynamic compaction. And this is the crater formation. So because of the deep dynamic compaction. And these are some advantages of dynamic compaction. This technique is especially useful if there is a huge area, say for example, greater than 5,000 square meters of the area has to be improved. So reduces the volume of the landfill waste, increases the in-situ density and collapse voids. So these are there are several merits that you can go through this slide or this video. And applications: ports, airports, heavy storage facilities, landfills. So especially where these facilities need to be created on loose granular soil deposits. This is the most important one. So this technique is especially useful to densify the loose, free draining, granular materials. It is not useful for clayey soils. Now the so-called the previous two techniques like a sand drains and the stone columns, those are specifically meant for the clayey soils. But today what we are discussing is a technique which is exclusively useful for the loose sands, that is a granular material. Now this figure explains some kind of the mechanism by which the soil beneath the pounder so gets densified. So first of all, when very heavy weight is dropped instantaneously, it is obvious that it generates some kind of the shock waves. Or here we can correlate it with some kind of the shear waves. Those are those are like your relay waves, or you can see shear waves, and they will move both in every direction, all possible directions. So in the downward direction as well as in the lateral direction. But when they move, so they will literally shear the particle and compress them. But this happens instantaneously. And as a result of these waves, when they move, so they readjust the particles. They will rearrange the particles to new state or new position. So this readjustment creates some kind of the crater. Whenever the particles gets readjusted, so obviously its reflection is in the form of a dent or the deformation. So here you can see. So compaction of the fill or subsoil is achieved by rearrangement of the grains as a result of the shear strains induced by the impact of heavy drop weight. The moment you drop it, it creates some kind of the shear waves, that is relay waves or love waves, so on and so on, because these waves are remain confined to the only the surface. And here the degree of compaction is achieved depends upon the weight of the hammer that you have used and height of the drop. So these are the two fundamental factors so that impact the degree of compaction. However, if you look at holistically the overall ground, then you also need to take into account of another important factor, that is the space. Spacing also affects the degree of compaction. Now this is one of the very important slide where you can easily understand. So for example here, the topmost figure indicates the applied energy. So initially each step rise indicates one number of blow. So this is one number of drop, second number of drop, third number of drop. Okay, applied energy. So initially less than 100 ton meter per meter square, then increase it to 120, then increase it to 200. Now, as a result of the drop of energy, so you can see the increase in percentage volume change. For each drop, there is a definite change in the volume. So there is a percentage volume change increases. Percentage volume change increases. While at the same time, the reflection of the volume change is improvement in the form of a degree of liquefaction. So the degree of liquefaction at the end it should decrease. That means, so here the peak indicates the soil is more vulnerable for the liquefaction phenomenon. It is decreasing means when it is touching the x-axis, it indicates that the soil is no more able to undergo the liquefaction phenomenon. Okay. Well, similarly, as the soil is getting densified, it is obvious that its bearing capacity increases, as you can see from this picture. So for each drop, the bearing capacity increases. Okay. However, the bearing capacity improvement may not be instantaneous. It may take a little time because so it also takes some time for particles to get rearrangement or to relocate to the new position. So that's why here it is shown the bearing capacity increases with the time. Increases with the time. So there are two fundamentals thing that you need to understand. The first one is called as a dynamic densification, while second one is called as a dynamic consolidation. As I told, this technique is useful only for the granular materials. So when you use in case of the loose sands, this is called as a dynamic densification, wherein you are simply expelling out air from the soil samples and thereby you are achieving the higher dense state of the soil material. The people have also reported that the dynamic compaction can also be applicable in case of only for certain clayey materials, and there they call this phenomenon as dynamic consolidation. However, so they attributed the dynamic consolidation to two important things. That is, the moment you apply a very heavy drop or very heavy energy to the clayey soil material, there is a possibility of generation of the excess pore water pressure and dissipation of the same excess pore water pressure. So these are the two phenomena that are attributed to densification of the clay materials. But this is only few people have reported when compared with the dynamic densification. So very few people have attempted for the dynamic consolidation. And as for them, so there are four fundamental mechanisms involved in densification of the granular soil. Those are compressibility of the saturated soil and liquefaction, change of the permeability, and thixotropic recovery. So these are the four fundamental mechanisms are responsible for densification of the soil and thereby bearing capacity or the shear strength or less mitigation of the liquefaction, so on and so forth. So
Sir,
yeah.
sir, for consolidation, we require static load, na sir? Why it is named dynamic?
If you go for 1D consolidation, that is static loading condition. That's why it is called as a dynamic consolidation. The similar way of load is applied in case of the clay material, saturated fine grained soil. Just imagine, I told this technique is valid for granular materials. But what if I apply the same energy on the fine grained soil? So although not many people have attempted, but a few of them have attempted, like Minard and Bulls. They told that we can also consolidate the fine grained soil by dynamic compaction. So that's because of by the generation of the excess pore water pressure and its dissipation over a period of time. And
Okay, sir.
there they named it is called as instead of the 1D consolidation, they renamed it as a dynamic consolidation. Okay, yeah. Now, I told the mechanism of the deep dynamic compaction, but what should be my the improvement depth, and how shall I determine the improvement depth? So many people have tried to understood because the depth of the improvement varies from case to case. So therefore, case to case and from the soil to soil. So in such a case, how shall I design the dynamic compaction depending upon the variability of the soil type? So there, what people have done is they try to correlate depth of the improvement with the amount of energy that they have applied. So here, The square root of WH indicates the amount of energy applied, and dA is depth of the improvement. And when they equated with the one factor that is called as alpha. So here now this alpha has been related with the soil type. So thereby I have addressed the amount of the energy with the soil type and with the depth of the improvement. So therefore, when you are dealing with one particular soil type, for example, in this table, if you look at rock fill, the value of the alpha is 1. That means majority of the energy simply gets transferred to the soil mass or the rock fill. For example, if you go to soils with unstable structure, it is 0.5. That means only the 50% of the energy gets transmitted to the soil. That means remaining 50% is dissipated or dampened. That's because the soil type is able to absorb such amount of the energy. Now you also recall our very initial lectures, especially the clayey soils able to absorb the energy and they can also store the energy. But granular materials, they neither absorb the energy nor store the energy. That's why the value of the alpha is very high. So if you look at very carefully, more the fines fraction of the soil, the higher is the value of the alpha. If you move towards the finer soils, the value of the alpha is quite less. Okay, so that's what you can notice from this table. Now this is since it is a little impossible to understand clearly. Now somebody also tried to characterize or categorize the soils into different zones depending upon the permeability. So line 1, zone 1, pervious soil where the plasticity index is 0 and highly permeable soil. So these are the excellent materials for deep dynamic compaction. Zone 2, semi-pervious soils. It comprises of some finer fractions where the plasticity index is less than 8 and the permeability varies from 10 power minus 3 to 10 power minus 6 centimeter per second. Zone 3, impervious soils. So it is obvious that the zone 3 soils are not at all fit for the deep dynamic compaction because they are impervious. Impervious means they comprise more of the clays, as you can see from this above table. And here it is also given what would be the approximate percentage of ground subsidence depending upon the soil type and in which zone it is falling, either zone 1 or zone 2 or zone 3. The objective of dynamic compaction is to increase the in-situ density, improve the bearing capacity and consolidation. So way back also we have discussed about the same thing. Then this is another important slide that you need to understand for what type of the soil it is most suitable. So this categorically says technique is most effective for coarse, free draining granular soils, whether well or poorly graded, it is immaterial, saturated or not. If the material is coarse, free draining granular soil, it is excellently useful. Cohesive soils tend to absorb the energy and thereby limit the technique's effectiveness. So not recommended for clayey soils with high plasticity index, that is greater than 8 or high degree of the saturation. So this technique is specifically suitable for the rock fills and gravels. As I told, these rock fills and gravels perfectly show the properties of the free draining with boulders and of refuse and waste tips are natural heterogeneous coarse materials. All are granular soils. Saturated very fine sands, silty sands and silty clays may not respond well according to permeability and cohesion, but such materials in part saturated fields have been successfully treated. But this is sporadic, means very rare. Okay, so you cannot say that every kind of the fine sand, every kind of the silty sand, every kind of the silty clay can be treated using the dynamic compaction. May not be. So you need to be little cautious. Alluvial clays, unsatisfactory, so not recommended. The most commonly treated soils are dumps. These are artificial made fills, simple soil dumps, and granular virgin soils. Soils below the water table are routinely treated. But these should be again granular soils. So careful control has to be used to allow dissipation of the excess pore water pressure created during the weight of the draft. This dissipation is possible only in case of the fine sands. The groundwater table should be at least 6 feet below the working surface for the process to be effective, which otherwise, so the groundwater may absorb some amount of the energy. So in organic soils, dynamic compaction has been used to construct sand or stone columns by repeatedly filling the crater. That means in case of the organic soils, you need aid of another technique to increase the efficiency of the deep dynamic compaction. And here this also shows another suitability depending upon the soil type. So for example, if you are dealing with the gravel and sand with less than 10% silt and no clay, so expected improvement is excellent and typical energy required is 2 to 2.5 ton feet per cubic feet. Sands with 10 to 80% silt and less than 20% clay, but PI is less than 8. Moderate if the soil is in dry state, minimal if it is in moist, and amount of energy required is 2.5 to 3.5. Fine grained soils with a plasticity index greater than 8. So the technique is not at all applicable. So therefore no point in talking about the energy. Landfills, so excellent, and amount of energy required is 6 to 11 ton. Now one particular thing you can notice from this table is as the fines content in the soil increases, the amount of energy required also increases. This is what you need to understand. So fills means more heterogeneous and fine grained materials. So therefore more amount of energy is required. So you can also calculate energy using this simple formula. And this is the stages how we do the deep dynamic compaction in the ground. First of all, so prior to commencement, you need to make a 1 meter thick blanket layer, and on top of it, we do the deep dynamic compaction. Then you also need to determine the number of passes. That means at a given location, do we need to drop only once or only twice or only 5 times or 10 times? Then how many number of again do we need to come or not? Those are called as a number of passes. So then subsequent passes compact successfully. So as shown in this picture, shallow layers following which the site is regarded. Now when I go for the compaction, there is two variety of the compaction. So first, my intention is to target deeper depths, and in a second phase I can compact only the shallow layer. Okay, I will show you more schematically in the subsequent slides. Now this is what exactly that happens. So right beneath the tamper, so you can see this is some kind of the zone of influence area. So suppose if you take the different zones, so this creates some kind of heave right adjacent to the crater, so all surrounding the crater. But at the same time, since the amount of energy applied is so enormous, it is obvious that the soil already fails under bearing capacity condition. Okay, but that is limited to only the shallow depth. It is not the deeper depths. At the deeper zone, the soil gets densified. At the shallower zone, the soil is completely fails under shearing condition. As you can see, this is potential slip surface. Now, so what happens if I at the same location, if you apply the so many number of blows here as shown here, like 1 number of blow, 2 number of blow, 3, 4, 5 number of blows. So the soil turns from the say for example recovery state to non-recovery state, and these are the volumetric strains. 1 number of blow, least volumetric strain, but as you go for 5 number of blows, there is a huge amount of the volumetric strain or the volume deformation. And in fact, this slide would give you the perfect understanding how the deep dynamic compaction is different than the conventional consolidation. So here there are two graphs which has been shown. One with dark arrows. So this dark arrow indicates the consolidation by the one-day consolidation. But the same consolidation can be achieved, or in fact same densification can be achieved by the deep dynamic compaction. Here the sudden drop indicates the drop of the heavy weight at a particular location. Here you can understand how much is the volume change. That is change in the wide ratio. There is a sudden decrease in the wide ratio. But at the end, so the total final degree of the improvement is remains same that of the one-day consolidation, and it has to be. This I will leave it. Okay. Now this is another important. So all soils may not respond in a similar way. So therefore, how shall I understand what would be the depth of the influence depending upon the amount of energy that is applied? So this graph would show you what happens to the different soil types. So, or how the depth of the improvement or the depth of the influence shall be determined based on the amount of energy applied. So this is another fundamental reason. So a factor called as alpha has been introduced for the soil type. So it could be 0.375 or zero point 0.5 or 0.7. So 0.375 means the soils are dominant with the fines fraction. Here you can see predominantly cohesive soil. Then silty soils, fields and rubble. Then full depth of the improved zone undetermined. Okay, now so far what we are discussing is about the deep dynamic compaction. Now the next question comes is, how shall I ascertain that so the ground has achieved a desired degree of the compaction? That means you need to do post compaction some kind of the testing. So that testing can be in the form of a either SPT or CPT or pressure meter test. Once you ensure that the entire ground has been improved by the deep dynamic compaction, as a next step, so in order to assess the degree of the improvement at the site where the deep dynamic compaction is applied, you try to conduct the SPT and keep on measure the SPT value. If you can able to compact, if you can able to perform the SPT. So in case if such facility is not available, alternatively you can go for the cone penetration test. So, or if your purpose is entirely different, then you can go for the pressure meter test, depending upon your requirement for which the site is meant for, or depending upon the importance of the structure. So, yeah. So this is a live demonstration, live demonstrated data. You can see here what has happened to the SPT N value before dynamic compaction and after dynamic compaction. So almost the SPT got improved by double. Similarly, you can also understand how the cone penetration value has increased pre and post dynamic compaction, and similarly the PMT. So the difference in these values clearly indicates that the entire site got densified. So this is how you will assess the degree of or the ground improvement or the site improvement or the degree of the improvement. So these are pressure meter test. This is complete setup for pressure meter. So just for the sake of visualization, I have included this slide, and this is the graph, a typical graph that can be obtained when you conduct any pressure meter. So this is a flat dilatometer, and this is shear wave velocity test, pre and post. Okay, so that's what the theory about the dynamic compaction. Now let us go to the design considerations. This is very simple technique. There is not much things are involved. So when I talk about the design considerations, so a few parameters comes into the mind is, first of all, what should be the spacing between two drops? Then what should be my depth of the influence? Then how much amount of energy shall be applied? And how many number of drops shall be at a particular location? So these are the different design parameters. When I looked into the literature, I found there are two variety of design methods are available. The first one is proposed by the Poran and Rodriguez. There is another method. This is very simple method. First, let me present this one. The Poran and Rodriguez. So they have assumed the improved zone some kind of a semi-prolate spheroid as shown here. This is the approximate shape of the area of the soil or impacted area, approximate shape of the impacted area. So if you look at the top view, it is a circular, while if you look at the side view, this is some kind of the spheroid or semi-prolate. But it has to have some kind of the geometry where the diameter is 2 times of A and the depth is B. So these are the designations given by the Poran and Rodriguez. And based on the huge data that they have collected, they try to develop this kind of a graph. In fact, this graph will be provided in the exam also. If you look at this graph, there are on the ordinate of left side, it is a function of the B by D. On the right side, it is A by D. And the y-axis, the x-axis is NWH by, in fact, let me show NWH by AB. So all parameters are defined. Now, as per Foran and Rodriguez, so they have given some kind of the design steps. Step 1, try to calculate the depth of the influence using the approximate equation of half square root of WH into H, where WH is the mass of falling weight in metric tons and H is height of the drop. So if you decide the weight of the rammer and height of the drop, then I can able to determine the depth of the influence. But in reality, it is the reverse. I know the soil profile. My aim is to improve the soil for a 10 meter or a 15 meter or a 5 meter. So therefore, my depth of improvement is fixed. So next parameter is usually all the devices comes with a specific weight of the hammer. So if I fix the weight of the hammer and if I fix the depth of the improvement, then I can calculate what should be the height of the drop. So, but normally when we study in a theoretical way, we go in a reverse way. So step 2, from the side view, B is equal to DI, that is depth of the improvement, where D is width of the hammer, if not circular in cross section, A is equal to area, cross section area of the hammer, and N is equal to number of required hammer drops. So calculate from the step number 2 depth of the improvement. In fact, we have calculated already DI from the step 1. Now you say assume that B is equals to DI. Determine di by d is equals to b by d. Di by d, where d is the width of the hammer. Now say di by d is equals to b by d. So b by d. So from this b by d, what I can do is corresponding to a by d or b by d, using the above graph, determine the value of the NWH by AB. Suppose from step number 3, if I know the b by d value, so draw an horizontal line onto the b by d graph, and from there you drop it a vertical line onto NWH by AB. So therefore, if I know b by d, I can able to pick up the value of the NWH by H into H by AB. So that's what is the step number 4. Step number 5, with the known values of the NWH by AB, determine A by D, and thus, so if A from the chart. Now once this value is known, now we need to adjust. Suppose if you look at this equation, I know the W, I know the H, I know the cross section, I know the B. In this NWH by AB, only unknown is N, that is the number of drops. So based on the B by D, if I pick up the value of from x-axis and equate to NWH by AB, I can able to calculate the N value. But this N value shall be a non-decimal value. So therefore, determine the N and round it up to some particular value. From that, once it is fixed again, then again recalculate NWH by AB. For corresponding to that value, draw another vertical line onto another graph of A by D. Okay. So for the calculated value of NWH by AB, pick up the value of the A by D from the right side ordinate. Okay. So from the A by D, I know the D, I want to calculate the A value. So here A is nothing but approximately half the spacing required. A is equals to half the spacing required. So A is equals to SG, that is grid spacing. The grid spacing SG required for dynamic compaction may now be assumed to be equal to or somewhat less than. So this is how. So this simple method has been recommended. This I will leave it. Yeah, but there is another procedure which is elaborately given by somebody. So these are the so many number of steps. So first of all, as per this method, you need to identify the zone category, soil type. So this already we have discussed, whether the given soil or your site falls under zone 1, where it is a pervious soil with PI is 0 and permeability greater than 10 power minus 3, or zone 2 or zone 3. Identify under what zone your soil type is falling. This is the first step you need to exercise. Second, So depending upon the identified soil type from the previous slide, like here I know the zone 1 pervious or semi-pervious or impervious. So depending upon the soil type, so pick up the value of the alpha, which is also called as NC, alpha or NC. So different people have given different designations, so don't get confused. Depending upon the soil type. Suppose if the soils are the pervious, that is granular soils, you can take NC as high as 0.5 and as low as 0.5 to 0.6. Okay. Then if it is a semi-pervious deposit with Pi less than 8, you can go for as high as 0.35 to 0.4 or as low as 0.4 to 0.5. Semi-pervious deposits, primary clays with Pi greater than 8. So the technique is not recommended, but if it is a low, then 0.35 to 0.4. Okay. So after identifying the soil type, pick up the value of the NC. Pick up the value of the NC. Once NC is known, so put that in this equation, that is Di is equals to NC into square root of Wt into Hd. So I know the NC depending upon the soil type. I have already fixed the rammer weight of the tamper, and I have already fixed the height of the drop. So I can calculate the depth of the influence. Depth of the influence. Next, the drop height and energy. So that is one way. The second way is, can I able to determine the drop height and energy alternatively? So that can be determined. So using this equation, Mainly et al. Provided a relationship between weight of the tamper and the drop height based on the field data. So as per them, the equation is to determine the drop height HD is equals to, it is approximately W2 into HD whole power 0.54. But you know the product of W into H is nothing but the energy for drop of the hammer. Drop of the hammer. So which is determined from the depth of the improvement equation. So as shown in the previous slide. So Wt into HD, Wt into HD, which is nothing but your depth of the improvement. Depth of the improvement. So dA is equal to NC into, so square root of W2 into HD. Okay, so the calculated drop height so may be adjusted based on the available tamper owned by the contractor. So if you know the depth of the improvement, or if you have calculated based on the energy, then again you can also recalculate what would be the drop height. What would be the drop height? Then another important parameter is what kind of the pattern and the spacing. Because if the spacing is too large, then in between soil might not get densified. If the spacing is too low, then the cost is astronomically high. So therefore it should be very optimum. So there are two phases of compaction. Phase 1 is meant for densifying the deeper soils, while phase 2 is meant for densifying the shallower soils. That is, there is another word that is called as ironing. Ironing means flattening the soil. Flattening the soil. So suppose if you look at the bottom diagram, you can see the phase 1 is meant for densifying the deeper soils. Phase 2 is also meant for the deeper soils, but not that much like a phase 1. While the phase 3 is meant for so ironing or leveling the soil. Ironing also called as a leveling the soil on the ground surface. On the ground surface. Now either you can go for the square pattern or the triangular pattern. And there are some guidelines like as per Lucas, maximum improvement is between di by 3 to di by 2. Spacing ideally 1.5 to 2.5 times the diameter or width of the tamper. Here suppose if you are going for the square pattern, there are two spacings S1 and S2. So these are also you need to think of. So phase we have already discussed this part. Now this clearly shows the first phase, compaction of the deep layer, second phase, compaction of the intermediate layers, and third phase, leveling phase, compaction of the surface layers. So you can easily understand that when I have compacted the soils at the deeper and intermediate layers, the top soil gets very loosened. Okay, that again need to be little bit densified. So that densification can be done by some kind of the ironing. So for leveling phase or ironing phase, it may not necessarily by the dynamic compaction. You can also use some alternative techniques. So like impact compaction or the rolling, etc. So these things also can be done. Now, alternatively, can I able to determine the depth of the crater? For example, if you look at this schematic diagram, so here you can easily identify. So right on the ground surface, there is a formation of a crater, and right beneath this crater, you can find the compacted area. Compacted area. So it is obvious that the energy transfer happens in the form of a triangular load distribution or the dissipation. So therefore, up to certain depth, it typically follows the triangular. Thereafter, there is certain dissipation. Or typically, if you take the bearing capacity theory or the pressure bulb theory, it is more or like a pressure bulb. And you can use this simple equation for a rough estimate. The depth of the crater DCD can be determined using this equation. DCD is equal to 0.028 into ND power 0.55 into square root of W into H, where ND is equal to number of drops. So depending upon the number of drops, you can determine what would be the depth of the crater. So this is a rough estimate, and if you want more accurate, then you can use this equation. Then how shall I determine the number of drops at a particular location and number of passes required? So that depends upon the amount of the applied energy. So the amount of the applied energy. So here the number of passes or the number of drops are correlated with the applied energy AE. So AE is equals to ND into W into H by AE. So ND means number of drops, which are typically 5 to 10. W known, H is known. AE is zone of influence. This is very similar to your pattern. A is equal to S square for square pattern, 0.867 S square for equilateral triangular pattern, where S is the drop space. But one important thing is that when I talk about the applied energy, so this applied energy shall be related to the depth of the influence. So therefore, they have redefined another term that is called as unit applied energy, UAE, which is nothing but the applied energy divided by the depth of the influence. But if you recall the number of phases, there are two phases that we have discussed, or in fact three phases. But deeper and intermediate can be clubbed as a one phase, and ironing phase can be taken as a separate phase. So therefore, energy required for the deeper compaction and energy required for leveling, that is called as ironing phase. So therefore, unit applied energy is nothing but energy required for the deeper dynamic compaction plus energy required for ironing. And here this table, maybe you need to remember, okay, what would be the unit applied energy required depending upon the soil type. Suppose if it is a pervious soil, grained soil, then unit applied energy is 200 to 250 kilojoules per cubic meter, and which is approximately how much in terms of the percentage of the standard Proctor compaction energy. So 33 to 41. And if you are dealing with the semi-pervious fine grained soil, then amount of energy required is higher than the pervious coarse grained soil. That is, here in this case it is 250 to 350, and if it is landfill, it is 600 to 1100. Okay, now I also reiterate, as the soil is becoming the finer and finer, more and more amount of energy is required. Now this table, the importance of this table is that when you design the deep dynamic compaction, you can directly pick up this unit applied energy, and it can be distributed between ironing phase and the high energy pass. So that the same thing has been done here. Now you see ironing pass. So applied energy for ironing pass is nothing but unit applied energy multiplied by the depth of the crater. Now from this table, I can pick up the unit applied energy, and I can able to determine, by determining the depth of the crater using this equation, amount of energy required for ironing phase. So then once I know the ironing phase, so I can equate this to NdWH by AE. So here everything is known parameter except ND. So therefore I can determine number of passes for ironing phase. So from the required unit applied energy in table 3.1, this is table 3.1. The AEIP in equation 3.2, total applied energy using the equation 3.21. So this is 3.21, and the number of drops using 3.2 for assumed one pass can be calculated. So if ND at one location in a single pass is too large, greater than 10, or depth of the crater is too deep, operation of compaction should be divided into two or multiple number of passes. So this is another guideline. So when you have substituted applied energy into this equation, into 3.2 equation, if ND is coming out to be greater than 10, so instead of going for a single pass, you can divide that into two number of passes. That means first you apply, say for example, you got a 12 number of blows. What you can do is in a first phase 6 number of blows, and come again in a second phase another 6 number of blows. And once that design is done, then how shall you decide the degree of the improvement? So it depends upon the several parameters like the soil type, how much would be the fines content, what would be the depth of the groundwater table, and what would be the amount of applied energy, drop layout, and time, so on and so forth. So there are some guidelines which has been given, again depending upon the soil types. Okay, suppose if the SPT on post compacted soil you are finding 40 to 50 means okay, it is improved to the desired degree. Or we have conducted the cone penetration test, and if you are getting the QC between 90 to 29 means okay. So we can presume that so the pervious coarse grain soil has been achieved to the desired degree of the improvement. So these are some kind of the guidelines. The same thing, I will just skip it, these one. Yeah. Now, how shall I calculate the amount of the settlement? Because this is also one of the important factors. Because if I don't calculate, then there is certain kind of mismatch. Certain kind of problem in a sense. Once it is compacted, there is a huge reduction in the volume, and this volume shall be recompensated by the blanket layers or some kind of the filling material. So therefore, for that purpose, you need to have a very fair idea what would be the net induced settlement on that particular ground. So there are no equations which has been given, or rather some guidelines were given by Mosley and Kirsch's. So approximate induced settlement as percentage of the improvement, depth of the improvement. For example, when you are dealing with the natural clays, so the approximate induced settlement is 1 to 3% of the depth of the improvement, and clay fills 3 to 5% of the depth of improvement, and natural sands 3 to 10%, granular fills 5 to 15, and controlled fill 5 to 20. So here also it is very clear from this table. As the soil comprises of more and more fines, the amount of the settlement is lesser. Yeah, one of the important thing that you need to understand about the deep dynamic compaction is, since you are impacting the zone with huge amount of the energy, and there is some kind of environmental hazard. So that's because of the vibration which has been created because of the drop, or the noise which has been created because of the drop, or the lateral movement of the soil as a result of the drop, whatever it could be. So to understand this one, you need to calculate a particular parameter that is called as the peak particle velocity. So this is the most important. So to understand, is there any impact of the my dynamic compaction and the right adjacent structure? So you need to compute a parameter called as the peak particle velocity. So depending upon the amount of energy that you are going to apply, so here it gives what would be the velocity of the soil or velocity of the wave that is passing through. If the velocity exceeds certain value, then it could cause damage to the adjacent structure. So therefore, they have given some threshold peak particle velocities. So suppose when you are dealing with deep dynamic compaction in the areas where it is a commercial or industrial, the peak particle velocity should not exceed 20 to 40 millimeter per second. Or if it is a residential, it should not exceed 5 to 15. If it is a sensitive area, 3 to 5. Just see. So how the limitations are imposed on the peak particle velocity, and what is the implication or the application of it, or what is the significance of the peak particle velocity? It could cause disturbance to the resident people or disturbance to the industrial activity. So for example, here you can see if the particle velocity is approximately 0.8, it is slightly perceptible. That means almost you cannot notice it. But between 2 to 0.8, it is distinctly perceptible. That means you feel it. Then above, you strongly perceptible, disturbing, and very disturbing. So in case of very disturbing, do you dare to do dynamic compaction in that area? Possibly no, because there is a possibility of the legal issues. So that person can go to court and complain, make a complaint. Then you will be in a big trouble. So therefore, you need to fairly understand what would be the peak particle velocity, and thereby what would be the environmental hazard to the adjacent structure or adjacent people. So this slide will be most useful to assess such environmental impact and thereby take a genuine decision. Should I need to implement the deep dynamic compaction, or do I need to think of some alternative technique, so that there are no legal issues subsequently? So these are some guidelines. Mosley and Kidd suggested that the particle velocity at 2.5 millimeter per second annoys occupants of the building, and isolation trenches of 2 to 3 meter deep and 1 meter shall be constructed to cut off or minimize the surface waves. Suppose if you want to cut off the propagation of these waves, then better is you make a trenches of 2 to 3 meter deep and 1 meter wide. Lateral ground improvement. So dynamic compaction also induces lateral ground improvement, which may damage existing underground utility lines or buried structures. And so as per Federal Highway Administration documented that lateral ground movement at a magnitude of 19 to 76 millimeter was measured at a distance of 6.1 meter from the point of the impact. See how much is the displacement. Then field monitoring the ground vibrations and the movement is necessary if there are nearby buildings and are underground utility lines or structures. So these are some kind of the guidelines. Okay, it is not only the engineering that you are doing it, but the societal impact also you need to understand at the same time. Else you are inviting the problem. So this you leave it elapsed time. Okay. So this is what all about the deep dynamic compaction. If you have any questions, I can address in 5 to 10 minutes time. Anybody would like to ask any question?